So we look into torque. Torque is tau, which is r cross f, the vector product of radius and force, and tau is equal to rf sine of theta with n cap, which is the unit vector, the direction, and tau max can be rf, it can be rf if sine of theta is equal to 1, which implies that theta is equal to 90 degrees, which is the case for, let's say, the radius here and the force here, and the angle is theta, which is the right angle. So theta 90 gives sine theta 1, which makes tau to be rf as written here. F, as we know, is equal to ma, so tau is equal to rma, and a, as we know, is equal to r alpha. So in terms of now angular acceleration, tau is equal to r alpha, so tau is equal to mr square r square m alpha. Okay, and also, as we know, that I, the moment of inertia, is equal to mr square, so in general tau would be equal to I alpha. So this is an equation of interest. Product of moment of inertia and the angular acceleration gives us the torque tau, and the case can be extended for the rigid bodies, the collection of referential masses. So for rigid bodies, a rigid body which is a collection of masses, so we have it here, differential mass m1, differential mass m2, and so on, and r1 and r2, the radii. So tau is equal to m I ri square alpha in general. Okay, which means that for the differential mass, tau 1 is equal to m1 r1 square alpha, and for differential mass 2, m2 r2 square alpha, and for differential mass n, tau n is equal to mn rn square alpha. Yes, and all put in a summation operation, all put to sum, which means tau total is equal to tau 1 plus tau 2 plus up to tau n, which says that tau total is equal to m1 r1 square alpha plus m2 r2 square alpha plus up to mn rn square alpha. Alpha can be taken out, and differential masses and radii respectively can be added. So tau total is equal to alpha m, put to a summation alpha mi ri square summation I is equal to 1 up to n. Okay. Okay, so tau total in this case would be alpha I, as we know that I is equal to m r square, so I total would be m I r I square summation I is equal to 1 up to n. Okay, so this is very much the situation, and it's not an easy one, but approximated to a simplistic general form. Now we look into the angular momentum. Angular momentum. So angular momentum L is equal to R cross P, yes, which is L is equal to RP sine theta and cap, the unit vector, and L is equal to RP sine theta in the scalar form, and if theta is equal to 90 degrees, sine of theta is equal to 1, so L is equal to RP, yes, and P is equal to mv, the linear momentum. So L is equal to Rmv and v is equal to r omega, the linear velocity in terms of the angular velocity. So L is equal to Rm r omega, so L becomes m r square omega, and now I is equal to mr square, which is the moment of inertia, mass times square of radius. So L becomes I omega. So this is important, basic to knowledge, but very significant in terms of angular momentum. For the rigid bodies, we will look into the case of rigid body, angular momentum, rigid body. So the situation is very much the same. There are differential masses m1 and m2 with the differential radii m1, r1 and r2, so and so on. So Li would be equal to mi ri square omega, yes, and it says that L1 is equal to m1 r1 square omega, and L2 is equal to m2 r2 square omega, and L and so on becomes mn rn square omega. And in this case, the total angular momentum would be m1 r1 square omega plus m2 r2 square omega plus up to mn rn square omega. So L total is equal to omega, the angular velocity taken out, and summation I is equal to 1 up to n m I r I square, yes. and I is equal to I total is equal to MIRI square. Yes, so we substitute, and LT is equal to omega. LT is equal to, yes, omega I T, or L is equal to I omega. Yes, the uh, angular momentum is equal to moment of inertia into angular velocity in general, if approximated into a sum. For the for a rigid body, and it has the differential masses and respective radii, which are collected into a summation. Yes, so yes, so this is interesting. And now we look into torque with respect to momentum. Torque with respect to momentum. Okay, torque with respect to momentum, tau is equal to r cross f. Tau is equal to rf sine theta, and if theta is 90 degrees, sine theta is 1. uh, r is perpendicular to f, so theta is equal to 90 degrees, sine theta is equal to 1, so tau is equal to rf basically, and f is equal to delta p by delta t. Rate of change of momentum with respect to time is force. So in the torque, we put the substitution of force r dot delta p by delta t. So now r delta p can be approximated to delta rp. So this is a rough approximation, but this is required here, so we have nothing else to do. We have nothing else which is doable except this substitution to reach the conclusion required. So what else is to be done? So tau is equal to delta rp by delta t. Okay, which is approximately equal to delta L by delta t, which says that rate of change of angular momentum with respect to time gives us torque. This is an equation of interest, and a critical point is the approximation r delta p is roughly equal to delta rp. R is the radius, p is the linear momentum. So this makes it possible rotational kinetic energy now. Rotational kinetic energy. Yes, kinetic energy Ke rotational is equal to what? Kinetic energy translational basically is equal to, as we know, 1 by 2 mv square. Yes, and v is equal to r omega square. V is equal to r omega, linear to angular velocity. So we put the value of for rotational kinetic energy. We put the value of v is equal. We put the substitution for v, which is r omega into half mv square. half m dot r omega whole square. So Ke rotational is equal to half m r square omega square. Okay, now this is important. Kinetic energy rotational is equal to 1 by 2 I omega square, because I is equal to mr square. The moment of inertia is equal to mass times square of radius. So this gives us the rotational kinetic energy, and for the rigid body it is not very different. For the nth differential, the kinetic energy is 1 by 2 I 1 by 2 omega square I n, or general form Kei is equal to, for the differential mass, 1 by 2 omega square. Angular velocity is approximately the same, so half omega square into moment of inertia of the differential. Okay, so what it means is that Ke1 is equal to 1 by 2 omega square m1 r1 square, and Ke2 is equal to 1 by 2 omega square m2 r2 square. And the form is something like this: m1 and m2, the differential masses with their differential radii in a rotation. So so the total kinetic energy for let's say for the nth differential, 1 by 2 omega square m n r n square. Yes, so the total would be summation of all Ke1 plus Ke2 plus Ke up to Ke n. Yes, so this means that Ke total is equal to 1 by 2 omega square m1 r1 square plus m2 r2 square plus up to mn rn square. So that gives us the total moment of inertia: 1 by 2 omega square I total, as I total is equal to summation I is equal to 1 up to n m I r I square. Yes, within the brackets it's summed. So basically kinetic energy rotational is equal to 1 by 2 omega square dot I. So this is an equation of interest for us. And now we have the cases for elevator. The case for elevator: Elevator is important in mechanics. uh, in an elevator, the